good evening, everyone, and welcome to the last in our series of Science Times, Exploring Frontiers of Science. I'm Dr. Mark Brannon, and I'm the president of the Princeton Adult School, and I welcome you all to this last lecture. I'm just going to have one or two things to say, and then we'll get to the business at hand, and John Burkhalter will be introducing our speaker tonight. First of all, I really enjoyed this lecture. I hope this series, and I hope everybody has as well. I think it's been it's been really a splendid lecture. And for those of you who come in, I suspect that almost everybody has a yellow sheet, but if you happen to come in and missed it or came in a different door, please pick one up there at the main entry. And if you can, fill it out before our speaker speaks, but fill it out if you can tonight, and leave it up there. Or it's a self-mailer on the back. Just fold it over and put a stamp on it, and it'll get to the right spot. But we do value your opinions and your evaluations very much, and we use them in trying to plan for the future. And that's the second and last item on my agenda to talk about. We're going to go back to the naming of the lecture series as the usual name, the Anne V. Shepard Lecture Series. As you know, this semester it was named the Aaron Lemnick Lecture Series, outstanding scientist at the university and a great friend and supporter of Princeton Adult School. The Anne V. Shepard Lecture Series for the fall of 2012, as you've seen, is going to be on the theme of Islam. We in the lecture committee talked about a lot of different subjects, and we took suggestions from people from the last couple of semesters, and we decided that this is such an overwhelmingly important topic that we are rich with speakers of great experience to talk to us. So as you can see, and I won't read this because you can read it yourself, but we also have this flight sheet that's up there if any of you missed that. And it gives you the dates and the names of the speakers. Some are just outstandingly well known in their field on Islamic studies here at Princeton University as well as at Rutgers University. We have a non-academic person, Karen Elliott House, that many of you may know, former publisher of the Wall Street Journal. And is about to publish a book on Saudi Arabia, which will be one of the speakers as well. We really hope to see all of you here for next semester. And please spread the word of what the topic will be and to your friends and neighbors. And again, we'll look forward to seeing you, and thank you for coming to this semester. Now, let me turn over the microphone to John Burkhalter, one of the members of our board of the Adult School.
Thank you very much, Mark. It's my happy opportunity this evening to introduce David Spergel, Charles A. Young Professor of Astronomy on the class of 1897 foundation, Professor of Astrophysical Sciences, and Chair of the Department of Astrophysical Sciences. David Spergel's honors are numerous, his publications extraordinary. Among his great honors recently, the 2010 Shaw Award, which honors individuals regardless of race, nationality, and religious belief who have achieved significant breakthrough in academic and scientific research. The Shaw Prize consists of 3 annual prizes: astronomy, life sciences, and medicine. As we can readily see, his interest in astronomy began at an early age and amplified by coursework and research work as an undergraduate at Princeton. As a junior at Princeton, James Binney introduced him to galactic dynamics. As a senior, he went to the Very Large Array, a radio telescope, where he was able to observe protoplanetary nebulae, the last gasp of a dying star. After graduating Princeton, he went on to Oxford, working with James Binney on dynamics. Following Oxford, on to Harvard, where he did thesis work, speculating about potential astronomical and experimental signatures of dark matter. Current undergraduate experiments are still looking for the annual modulation effect that he predicted in this very thesis. John McCall brought him back to Princeton as a long-term member of the Institute for Advanced Study. And while at the IAS, supernova 1987A exploded in the large Magellanic Cloud. And he spent much of the first year at the Institute thinking about the first detection of extrasolar neutrinos. Leo Blitz introduced him to galactic structure. His first study of the millimeter sky, but with a focus on modeling our galaxy rather than the cosmic background radiation. Work showed that the Milky Way is a barred galaxy. In 1987, David joined the Princeton faculty. In his early years at Princeton, he explored the idea that phase transitions on the early universe could generate density fluctuations that grew to form galaxies. When COBE, C-O-B-E, the Cosmic Background Explorer, reported its results in 1992, David would write as follows: I realized that these models were ruled out. While these models were not successful, exploring alternative ideas is an essential part of science and provided my own introduction to the cosmic microwave background. Stimulated by the claims that COBE proved that the universe was flat, he began studying curved universe models. While the COBE data did not rule out negativity or positively curved geometries, he recognized that higher resolution measurements could determine the shape of the universe. In 1994, he was offered what he has written, the greatest scientific opportunity of my career. I was invited to join a team of scientists who were proposing to build a next generation satellite to observe the microwave background. Prior to joining this team, almost all of my work, as David has written, was done with small groups of theorists or as a single author. Working with WMAP, the Wilkinson Micro Anisotropy Probe, tongue twister, has been my greatest scientific experience. Without the unique contributions of the many talented team members, WMAP would not have been a success. Professor Spergel feels very fortunate to have been able to look back into the first moments of the history of our universe. And we are grateful to him for sharing his insight and experience. Please welcome David Spergel to his topic, From Simplicity to Complexity, the History of Our Universe.
So it's a real pleasure to be here, and a real pleasure actually to be speaking in the series this year named after Aaron Lemonick. Aaron was the person who brought me to Princeton. He was Dean of Faculty when I joined the university, and he was the person who brought me to the adult school. He organized a series of lectures on the cosmos, and I spoke as part of that series a few years ago. And he was a terrific teacher, and I think a real model for members of the faculty like myself, for someone who really valued teaching, communicating science, both to the students here on campus and to the community at large. So I think it's a very nice honor to be the last lecturer in this series. So what I'd like to talk to you about tonight is mostly my adventure with the WMAP satellite and some other work we've done more recently, and talk about taking the universe's baby picture. And in fact, as some of you figured out, my mother, after hearing a version of this talk with this title, said, you've got to use this old picture. And scanned it in and emailed it to me, so there it is. So I was a student here and graduated in 1982. And when I was a student, I took the undergraduate cosmology course. And it's a course that I've taught many times since. And when I took the course, there were a lot of things we didn't know that we now know the answer to. And, you know, if there's one thing I want you to take away from this talk, is the sense of tremendous progress that we've had in the past 30 years, where we've really learned a lot about the history of the universe. Now, I'll conclude by showing you that while we've answered these questions, we have other, perhaps, I'd say more profound questions that we're left with. But we now know how old the universe is, its composition, its shape, and have a basic picture for how galaxies form. As I'll discuss in the talk, we know that the universe is about 13.7 billion years old. We know that with an uncertainty of only about 1%. So we sort of know where we came from when we've been around. To put that number in perspective, the solar system is about 4.5 billion years old. So our solar system has been around for a third of the age of the universe. Relatively recent, but not tiny compared to the age of the universe. Of course, the existence of multicellular life is perhaps only 1 billion years old, and humans have been around for a tiny fraction of this time. What we've learned about the composition of the universe has been surprising. Atoms, the stuff that makes up us, makes up only about 4.5% of the universe. The next 25% is made of what we call dark matter. That's stuff that behaves under gravity like ordinary atoms. It clusters in galaxies. But it interacts incredibly weakly with ordinary matter or with light, which is what we call dark. You can't see it. We don't know what the dark matter is. We have some ideas that are plausible. And one of the potentially very exciting things that might be discovered at the Large Hadron Collider or in an underground experiment is dark matter. So the dark matter is one where I think we might make significant progress on in the next 30 years, maybe in the next 5. What was really surprising to learn is that about 70% of the universe was made up of what we call dark energy. There seems to be energy associated with empty space. It's causing the universe to expand ever more rapidly. We don't know why it's there. The level we see is something we don't understand. The discovery of the dark energy was one of the great surprises of the past 30 years, and really one of the great profound mysteries of physics. My colleagues Saul Perlmutter, Adam Riess, and Brian Schmidt were just awarded the Nobel Prize this year, in 2011, for their discovery of this cosmic acceleration. We now know the shape of the universe. I'll talk a little bit more about this as the talk goes on. The shape of the universe is flat. That means that the geometry that we all learned in high school, when Mrs. Smith told us that the sum of the angles of a triangle is 180 degrees, that's true not just on the piece of paper, not just in 10th grade, but on the scale of the visible universe. And that has profound implications for the universe's composition and eventual fate. We have a basic picture for how galaxies formed. Tiny fluctuations in the first moments of the Big Bang grew to form galaxies. And the basic properties of these fluctuations were as simple as they could be. Their statistical properties are described only by 2 numbers. An overall amplitude, how lumpy the universe started out, and how that lumpiness varied with scale. So today, we have a very simple cosmological model. Everything that I'm going to talk about in this talk tonight, all the conditions in the universe, everything we observe, we can fit all of our observational data with 5 numbers. The age of the universe, the density of atoms, the density of matter, how lumpy the universe is, the initial amplitude of fluctuations, and how that lumpiness varies with scale. So there's two versions, I think, of thinking out where we are in cosmology. The glass is half full version is, I could explain all the data we see with 5 numbers. That's a pretty simple state to be in for simple understanding of the universe. The glass half empty version is, I don't know what makes up 95% of the universe. It's in some form of some stuff that we have no idea what it is. Or we have lots of ideas, almost certainly, almost all of them are wrong. So, we're at this moment in the field, and this is the story I want to tell, where we both understand a lot, but also understand how much we don't understand. So, to tell the story, I first have to teach you a little special relativity and a little general relativity. Let's start with special relativity. The important idea for special relativity is light travels at a finite speed, the speed of light. So when you look out in space, you look back in time. It takes light a few billionths of a second to get from you to me. So you don't see me as I am right now, but as I was a few billionths of a second ago. It's not very significant. I don't change that much in a few billionths of a second. But the further out you go in space, the further back you go in time. It takes light about 8 minutes to get from the sun to us. So we see the sun as it was 8 minutes ago. Jupiter takes about 30 minutes. So it takes light about 30 minutes to get from Jupiter to us. That's pretty significant when you send a probe to Jupiter. Because it takes, you want to tell the probe to do something, it takes 30 minutes to get the message there, 30 minutes to get the message back that it moved. It's like having a telephone call. You probably had this experience on a bad phone connection where it takes a second for the signal to get back, and you know how disturbing that is. Well, if you have a conversation with someone in Jupiter, it's 30 minutes. And the further out you go in space, the further back you look in time. And I guess I gave this talk last in Manhattan. I didn't change the slide. We look out to the nearest stars. The nearest stars are about 4 light years away. That means it takes light 4 years to get there. So you're sitting on a planet around one of those nearby stars. One of the remarkable discoveries of the past decade, not something I'll talk about today, but I've given other talks on, is we've discovered now thousands of planets around nearby stars. So if you're sitting on one of those nearby planets around one of those nearby stars, we see them, if there's life there, as they were 10, 20 years ago. If they're 20 light years away, they look back on us, they see us as we were 20 years ago. They see me with a full head of hair. So of course, the further out you go in space, the further back you go in time. When the Hubble telescope looks out at distant galaxies, it sees galaxies 12 billion years ago. So those galaxies are quite young. Some of the distant galaxies Hubble observes were around when the universe was only 1 billion years old. So as astronomers, we get to study the past by just looking out in space. And what's wonderful about looking at the microwave background, the leftover heat from the Big Bang, is we're looking out in space 13.7 billion years and seeing what the universe looked like only 380,000 years after the Big Bang. So now we have to turn to the Big Bang Theory. And I don't want to talk about the very popular TV show that describes some graduate students at Caltech. One of my friends at the Institute likes to say that this show isn't fiction, it's a documentary. I even know people who I think are remarkably like Sheldon. But no one at Princeton, only Caltech. So now that we've learned special relativity, we now have to learn general relativity. General relativity consists of two ideas. This is what Johnny Wheeler, who was my academic great-grandfather, taught me, and who was a long-term professor here. The two ideas of general relativity is matter tells space how to curve, and the curvature of space tells matter and light how to move. So if you have the sun here, it curves space around it. And the Earth tries to move on a straight line in that curved space, so it ends up on a circular orbit. Light gets deflected by that curved space. That's it. You now understand general relativity. You're all relativists. Now that you've got that down, you realize that all I need to tell you is how matter is distributed in the universe. And that tells you how space is curved. And that tells you the geometry and the fate of the universe. Now the hard thing about general relativity, the thing that most people find disturbing, is almost all of us have a Galilean notion of space and time. We think of space as absolute, kind of like a piece of graph paper, where I'm at coordinate 0, 0, and over here is coordinate 0, 1, and so on. Einstein taught us to think about space as relative, and to define the geometry of space by relative distances. I tell you, it took me, I flew in January from New York to London. Actually, I went to Stephen Hawking's Festschrift, celebrate his 70th birthday. I then, being the crazy person I am, 2 days later, hopped on the plane, flew to Tokyo. I was in Tokyo for 4 days. It took me, I guess, about 8 hours to get to London, 12 hours to get to Tokyo, and then from Tokyo, I flew back to Newark. That was another 12 hours. Just from telling you those facts, you know the Earth is round. It's a sphere. So just telling you the relative distances between objects, or the relative travel time, specifies the geometry. Relativists specify geometry in terms of observers. How long does it take light to get from me to you, from you to her, from her to me? When I talk about the universe expanding, what that means is not that we're being thrown out in an explosion, but we're all standing on the same spot, but the time it takes for light to get from me to you gets longer and longer. The effective distance between us grows. This is actually I think the conceptually hardest part of the Big Bang Theory, is to think about the expanding universe. The picture I have of the universe's expansion is to think about a balloon. And in doing that, I suppress one dimension. We live in a two-dimensional universe on the surface of that balloon. And you glue pennies onto the surface of that balloon. Those pennies are different galaxies. And that balloon's expanding. It's not expanding in space, it's expanding in time. So as your balloon goes outward, you're going into the future. And as your balloon gets blown up, the distance between those pennies grow. And that's the picture I have, at least, of the expanding Big Bang universe. Now you can run that picture back in time. You realize the balloon collapses down to a point. And when you collapse down to the point, that's the moment when the Big Bang began. And that's the image I have of the Big Bang Theory, which is kind of embedded inside general relativity. And the key idea, this goes back to Hubble, is the notion that we live in the expanding universe. One of the fun things I did recently, I'm still following up on this, is I found in a used bookstore in England over the summer, 2 summers ago, a copy of Henry Norris Russell's astronomy book from 1929. And Henry Norris Russell was the chair of the department here for about 40 years, leading figure in astrophysics in the pre-Second World War America. And in it, he reports about new results communicated before publication from Edward Hubble that describes the expansion of the universe. And it came out before Hubble's paper. It did. And, sorry, the book came out in 27, Hubble's paper came out in 29. There's a dispute going on right now about whether or not Hubble actually published the expansion first, or the work was done by de Sitter in Europe. But the fact that this book in 27 shows that Hubble was communicating to other astronomers in the United States about this, to me implies that Hubble really did discover it first. And one of the things I've been doing is looking through Russell's papers, because I suspect somewhere in Princeton is a letter from Hubble to Russell, written in 1927, which actually may be the earliest discussion of the expanding universe model, or the observations on the expanding universe model. Here's our picture today of the expanding universe model, showing the universe expanding in time going to the right. There's our microwave background as we go back, and here we are today. This is our satellite, the Wilkinson Microwave Anisotropy Probe, named after my colleague, late colleague and friend Dave Wilkinson, who was one of the leaders in the field of experimental cosmology, built, or one of the key people who helped build the COBE satellite, and he really was one of the people who spearheaded what was the development of what we then called the Microwave Anisotropy Probe. He passed away after we had begun analyzing our data. He had seen some of our initial results, and after we went to release our results, NASA very kindly let us rename the satellite the Wilkinson Microwave Anisotropy Probe. So there's what we call WMAP, looking out in space, back in time, looking back through the history of the universe, back to the microwave background, back only about 400,000 years after the Big Bang. We look out, we see the microwaves that propagate to us. And there's the satellite, there's David, and the satellite was launched actually quite far out in space. We want to be in an environment that was really quiet. We want to be somewhere where we were out there in orbit with both the Earth and Moon and Sun all behind us. So we went out to what's called the Second Lagrange point, about 1 million miles from the Earth, about 4 times the distance of the Moon, where the satellite was out there for 9 years, orbiting, taking these pictures of the microwave sky. And let me just skip to showing you what it looks like when we look at the microwave sky. This microwave background, this cosmic background radiation, is a leftover heat from the Big Bang. It fills all space. It's something that most of you have actually observed. Looking around the audience, I think most of you remember back to a time before we had cable TV. And you had a satellite dish. And your satellite dish meant when you turned between channels, you pick up static. Well, about 2% of the static that you saw between channels is the microwave background radiation. Most of it's static from the Earth, but a couple percent of it is leftover heat from the Big Bang. And it fills space. There's this stuff in this room right now. It's nearly completely uniform. It's actually discovered here in New Jersey by Penzias and Wilson, 2 scientists working at Bell Laboratories. And when Penzias and Wilson discovered this, everywhere they looked, they saw the same thing. Then over about the next 20 years, scientists worked very hard to look for tiny variations in this background. And about, they first discovered what's called the dipole, a variation at about a part in 1,000, so pretty small. Variations to the level of 3,000th degree due to our motion, that's called the cosmic dipole. And then when you remove the dipole, and this was what COBE, WMAP's predecessor, found, they found tiny variations in temperature at about a part in 100,000. So these tiny variations. You can think of just, looking at the Earth from space, it's mostly a sphere. Only when you look very carefully do you start to discover mountains and continents. And that's what we've done by looking at these tiny fluctuations. What's nice about doing that is we can use these fluctuations to learn about basic things like the geometry of the universe. Well, you're all general relativists, so you know that the amount of matter determines the geometry. If we live in a universe with a lot of matter, it curves space a lot. The geometry of space is more like a sphere. The sum of the angles of triangles on drawing a sphere is greater than 180 degrees. If you draw points on a sphere, so you try this on a globe at home, with New York and London and Tokyo, the triangle you make, the angles are bigger than 180. And if space was positively curved, if we sent light signals between 3 points, we'd find the sum of the angles of the triangle was greater than 180. That would correspond, this positively curved universe, to a universe that was very dense, one in which the energy in gravity, the gravitational energy, overcomes the energy in expansion. So that's a universe that will eventually collapse on itself. The other limit is what we call an open, or negatively curved universe. That's a universe in which there's not so much matter, so space is more saddle-shaped. You draw a triangle on a saddle, the sum of the angles of a triangle is less than 180 degrees. It's one that has, in which kinetic energy, the energy expansion, overwhelms gravitational energy. The boundary case, the intermediate case, is the one that has zero total energy. The positive kinetic energy and expansion is balanced by the negative gravitational energy. What's nice about looking at the microwave background is we can figure out the geometry of the universe. Because in these different models, the size of hot and cold spots would be different. If the universe was closed, the hot and cold spots would be about 2 degrees across. If it was open, it might be more like 0.2 degrees across. The flat universe makes a very specific prediction. The size of the hot and cold spots would be about 1 degree. And one of the primary goals of the satellite was to go out, map the microwave sky, this leftover heat from the Big Bang, and see how big those hot and cold spots are. So that's what we did. We launched in 2001 and went up on a delta. It was very exciting to go down to the launch and see that. And then the satellite's out in space, spinning. The key thing about the satellites is making differential measurements, measuring the temperature differences between 2 points on the sky. And mapped the sky and gave us these pictures of the sky. What you're seeing here is the whole sky around us. So this is like taking a globe and projecting it on a piece of paper. Now what you're seeing is the sky around us at different wavelengths. So this is what the sky looks like at the frequency of 22 gigahertz. The bright red thing across the center is the galactic plane. That's our own galaxy, the Milky Way. You're seeing hot gas and electrons in the Milky Way. You go to higher frequencies, the galaxy's not as bright. These mostly mottled blue and yellow stuff is the microwave background. Those are tiny variations in temperature, about a part in 100,000. That's the stuff most of us are interested in as cosmologists, not the bright red thing, our own galaxy. And as you go to higher and higher frequencies, the galaxy becomes less important. We can zoom in and actually measure the size of those individual hot and cold spots. And they turn out to be about 1 degree across. That's how we know the universe is basically flat. What we actually do is combine together all our data, try to make a clean picture of what this microwave background looks like. And this is our current best picture that we have of these microwave background fluctuations. Or at least the current best picture we have that's public. The Europeans launched a successor satellite a couple of years ago called Planck. And it's been mapping the sky at an even higher resolution than WMAP. And they have not yet reported their results. Well, I say the Europeans, it's a project that has very important US contributions. And in fact, Bill Jones, one of the members here at Princeton is the person who designed the detectors that are being used in the Planck satellite. And, well, I don't have a cleaner picture. Bill Jones actually does. So there actually is a cleaner version in Princeton. We used to joke with the supercomputers here in Princeton that the computers we have at the universities are the fastest computers in Princeton that anyone's allowed to talk about. For those of you who don't realize the joke, the NSA folks are here at Princeton as well. So you look at the sky, it's mostly a random pattern. But you can kind of zoom in, there's some interesting features. My favorite feature, if you look carefully enough, there's the letter SH. Now, I don't know what that means. It's most likely a cosmic coincidence representing the fact that our eyes are really good at forming patterns. But maybe there's some secret message. But we usually don't look for those patterns. What we actually do is we go to the map, and let me just describe the pictures. And we like to go, here's the pointer, and ask, let's draw a circle about this big, and ask what's the amplitude of fluctuations on this scale, how lumpy is it on this scale, now try a smaller region, and just measure the lumpiness as a function of scale. And that's what we've measured here. This shows how lumpy the universe is in millionths of a degree as a function of angle. So this is how lumpy it is. We call this is 180 degrees divided by the angle. So this is how lumpy it is on the 20-degree scale, the degree scale, and smaller. So you can see that the characteristic scale for the lumpiness is about a degree. That tells us the universe is flat. The points here are our data. And you can see there's a lot of structure here. That structure is due to the fact that we have sound waves in the early universe. And the fluctuations we see are their properties determined by the way sound waves behave. It's actually pretty simple physics. I'm not going to go into it tonight, but it really is freshman level physics at some level to understand the details of these fluctuations. And you can, the curve here is our model. And the model fits the data really well on the scales we've looked at and in this picture. And it's fitting this model to the data that gives us the basic cosmological parameters. And we found that the universe is remarkably simple in terms of its basic properties. So now that we've taken the universe's baby picture, we want to run the picture forward in time. So here are 3 randomly selected children. We run them forward in time to when they're half their current age, compare them to observations from Hubble, and then further forward in time to today. The picture seems to not be properly timed. But believe me, they evolve forward in time and get older every day. We do the same thing with the early universe. We take computer simulations, and we start with what we see in the WMAP data. We use the computer simulation to start with those initial fluctuations we see, and run it forward in time to predict the pattern of fluctuations that we should see in the large-scale distribution of galaxies. And what you see is from an initially very smooth distribution, lots of structure emerges. And you'll keep running the movie over and over again, you'll see clusters of galaxies. This will correspond to a cluster, and there's a galaxy there, and a galaxy there, and a galaxy there. And what we then do is go out and observe the galaxies. And the key to that is a project led by folks here, started by my colleague Jim Gunn, called the Sloan Digital Sky Survey. And here's the Sloan telescope. And what Sloan did was go out and measure the positions of over 1 million galaxies in the sky, and use that to measure the large-scale distribution of matter. And here's my student, Beth Reed, who's now at Berkeley. What Beth did was she did one of the analyses where you take all the galaxies, you measure how lumpy the galaxies are as a function of scale. The solid line is an extrapolation from the WMAP data to today. So we take what we see 400,000 years after the Big Bang. We want forward in time, predict what we should see, go out and measure it, and the distribution of galaxies are beautifully fit by the theory. When we look in detail, we actually see the patterns of ripples that we saw in the microwave sky. We even see them in detail in the galaxies today. So that gravity seems to explain all that happened. We're now in this state that I hinted at the beginning of my talk, where all the pieces fit together. We have observations of distances to galaxies from the supernovae. So this is a measure effectively of the distance as a function of redshift, how far back in time we go. The points of the observations here from the Hubble telescope, some on the ground here. The curve is our best fit from the WMAP data. And the supernova distances were led to the Nobel Prize this year. Measurements, the Hubble constant, how fast the universe is expanding. We can estimate that from our experiment. We find that the number we measure is 72 with an uncertainty of about 2. The Hubble telescope folks find about 73. So this is the kind of thing we can measure different things in the same way. Same thing in different ways. So another thing we measure is cosmic abundance, the abundance of elements. We can infer the density of atoms from our observations and measure it to about 5%. Our colleagues measuring the abundance of deuterium, a leftover relic, a fossil basically from the Big Bang. Most of the deuterium in the universe is made during the first 3 minutes of the Big Bang. They can also infer the density of atoms. Totally different method, totally different types of observations. They get the same number. The fact that things fit together so well has given us some confidence in our model. So today we have this standard cosmological model in which all the pieces fit. Atoms make up about 5% of the universe. Most of it's dark matter, rest dark energy. Now the interesting thing about scientific models, good ones, is they make predictions. So this is what our model predicts for the properties of these fluctuations. So here's the amplitude of the fluctuations versus scale. This is what we've measured from WMAP. We've measured these first 3 peaks seen in the microwave sky. Now the observations predict we should see more peaks. Here's 4, 5, 6, 7, 8. There should be small scale ripples if we could see them. And what we've been working on the last couple of years is looking for these small scale ripples predicted by the model that we fit the WMAP to. And to do that, we want to do that was we want to address questions like what's the dark matter? How did the universe begin? And we've been building an experiment, working on an experiment in Chile called the Atacama Cosmology Telescope. It's a project that's led by my colleague Lyman Page in the physics department, together with my colleague Susan Staggs in physics and some folks actually all over the world working on different parts of this project. And this is at a remarkable location. It's in the Chilean desert at about 5,300 meters, so 17,000 feet above sea level, up near the border with Bolivia and Argentina. It's an incredible site, very, very high, very, very dry. And here's the telescope being assembled. This is actually the telescope in space. A very good way to get a picture of your telescope looking up is go to Google Sky, type in the coordinates, and there it is. So there we are. It's about a 6-meter telescope looking out in space. And what it's doing is zooming in on a small portion of the sky and getting a detailed picture of what's there. So let me skip ahead a little bit. So 2 things we see. So one thing, I'll go back, it's so much fun. So this is what we actually see in the map. Here's these big lumps of the hot and cold spots we saw from WMAP. One of the nice things about zooming in is you discover some other interesting things. So you zoom in and you find this little blue spot here is a cold spot. That's because there's a cluster of galaxies blocking and it's basically casting a shadow against the microwave sky. And we'll actually go back and look at that object soon. And then we see some bright things where we actually have emission. And those emission, when you look at that in more detail, you often discover what you're actually seeing are some nearby galaxies, for example. And here's a nearby galaxy that we see from our Chilean experiment. And that's an optical image of that same galaxy. You can see that galaxy's got a lot of dust in it. And we're seeing the emission here from the dust. And my favorite object we found is an object that we've nicknamed El Gordo, the fat one. And my colleague Felipe Minato at Rutgers has really led the analysis of this. Felipe is Chilean, and when we discovered this cluster, which we think is actually the biggest cluster of galaxies known in the visible universe, it's has a mass of about 2,000 trillion times the mass of the Sun. So it's an enormous cluster of galaxies casting this enormous shadow in the microwaves. When we look at the optical, we can see the cluster is made up of many galaxies. And then we observe it in the X-ray. And we want to issue a press release for this. We want to come up with a good name for the cluster. There's one of the fun things you get to do if you discover somebody's name. So I kept saying we should name it El Gordo. We discovered it with the Chilean Observatory. It's so big, it's so we call it the fat one. And Felipe of the telecom got very upset. And it turned out that that was his nickname. He said, I'm not going to be called El Gordo again. We're not named it after you. It's the cluster. So, always interesting to see those childhood memories come back. So here's this enormous cluster. We've now been observing this in great detail, seeing lots and lots of galaxies. This is the wonderful thing about observing the oldest light in the universe. It has to pass through everything else in the history of the universe. So it's affected by it, and you can see its imprint in these clusters. But what I mostly wanted to focus on was how our model did. So that's our basic cosmological model making predictions. Remember, this is a model of just these 5 parameters: density of atoms, density of matter, how old the universe is, how lumpy it is, and how it varies with scale. And that same model fits the large-scale distribution of galaxies today. Well, we've collected the additional data. Not only have we collected it, our colleagues at University of Chicago, in a competing experiment, doing the same thing from the South Pole. We mostly looked at different regions of the sky, but sometimes we've chosen to check our results to look at the same region. And you can see when we do that, we see the same pattern in Chile that they see in an independent experiment in the South Pole. When we look at the statistical properties of the fluctuations, that's what we see. So the blue points, big blue is us, yep. The blue points are our measurements from Chile. The red points are their measurements from the South Pole. And the curve is the model. So that same basic model, these are parameters we say published in 2003, we compare it to the observations, and it fits beautifully. It suggests that it's doing pretty well, and that this basic story that I've been telling seems to hold together. We've been testing in other ways. So to give a sense of some of the things we've been doing lately, this is work being done right now by Blake Sherwin, who's a graduate student here at Princeton working with me. And he's been measuring gravitational deflection. Well, you're all general relativists. Let's go back to our general relativity. There's lots of massive objects between us and the microwave sky. They're going to curve space. Light moving through curved space gets deflected, the same way a lens would deflect it. In fact, when I look at the microwave sky, look out in a given direction, the light that I see didn't follow a straight line. It got deflected in its path from back there towards us. And that distorts the images, and distorts the images in a very predictable way. And what Blake has done is plotted here, don't worry about the axes, is measure the amplitude of those distortions versus scale. And our theory is the rate curve. And the points are some results we published last year, which is the first detection of gravitational lensing on these scales. And what this shows is that general relativity is correctly describing the behavior of light propagating for 13 billion years and being deflected on scales of hundreds of millions of light years. There's the Planck experiment, I mentioned that already. It's out in space, it's still taking data. We'll be reporting the results very soon. So, coming to the end of my talk, I want to leave some time for questions. So let me conclude. I hope I've left you with the sense that cosmology is really in a golden age. I feel very fortunate to be working in the field at this time, a time at which we've made tremendous progress. This progress has been driven both by theoretical ideas about what happened in the early universe and by experimental measurements like those I've described, from WMAP, from the ACT experiment, where we've been able to take the universe's baby picture and map what the universe looked like 13.7 billion years ago. And also driven by observations in the more recent universe. Things like these galaxy surveys, which have mapped out the distribution of matter in the nearby universe and shown, what's happened in the last billion years. And what's emerged from this is a coherent picture of how structure in the universe grew from its first moments to what we see today. And it's a picture that, as I've stressed a couple times, is both very satisfying. It's a very simple model, 5 numbers, reduced all the statistical properties of everything we see, but a model that has some very profound and open questions. I want to leave you with these questions. First, we talked about the fact that atoms make up only 4.5% of the universe. What's that dark matter? We don't know what it is. We're working very hard, underground experiments, astronomical measurements, the Large Hadron Collider, trying to find the dark matter. Dark energy. The universe is accelerating. There's energy associated with empty space. We don't know why it's there. It's probably telling us something is missing in our understanding of perhaps the connection between quantum mechanics and general relativity. So that's another profound mystery. Well, we understand how the fluctuations we see 380,000 years after the Big Bang evolved to galaxies. And we have some ideas for how those fluctuations are generated in the first moments of the Big Bang. We don't know the answer to, I think, the most interesting question, which is how the universe began. What was there before the Big Bang? Perhaps that's even the wrong question. Maybe that time itself began with the Big Bang. This final question is one that somewhat is philosophical, somewhat is a physics question. To the extent to which it's a physics question, one of the things we're trying to do is see if there's ways we can address this observationally. There are ideas about what happened in the first moments of the Big Bang. Ideas, for example, my colleague Paul Steinhardt has been an advocate of the notion that the universe did not begin in the Big Bang, but has in fact gone through multiple cycles. And that has gone through cycles of collapse, and then re-expansion, collapse, and then re-expansion. In that cyclic universe model, one of the predictions of that model is we should not be able to see any gravitational waves produced from the Big Bang. This model in which the universe began in the Big Bang predicts there should be a pattern of gravitational waves. What we're trying to do right now is detect those gravitational waves by looking at their signature in this big plateau heat in the Big Bang. We haven't seen them yet, but if we do, we'll be able to at least push our understanding of the beginnings of the universe further back. So let me leave you with those thoughts, that we've both made great progress in how old the universe is, but we're left, as we often are in science, having answered some questions, raising another set of questions, deeper and more profound, and questions that we hope that we and future generations of scientists we'll be able to make progress in answering. Let me stop there. Let me take some questions. Let me start in the back.
What is the multiverse, and is there any evidence for its existence?
What is the multiverse? Well, people use actually the phrase multiverse to refer to two different concepts, related in some ways. One idea is when we live in our universe represents one region that's expanding since the Big Bang. And there are other regions of space that are expanding. And these other regions are what we call causally disconnected from us. There's no way information that we can communicate with them or they can communicate with us. But there are many possible universes. And here's one that we exist in, and there's another one over here, another one over there, and there's perhaps an infinite number of different disconnected universes that are out there. I find the notion of the multiverse often crosses the line from physics to metaphysics and philosophy. I'm a nuts and bolts physicist. I like things you could test perhaps today or even in the distant future. That's one ideas that are capable of experimental falsification or verification. The notion of the multiverse is in many ways, in this formulation, by its very nature, untestable. The multiverse the notion of the multiverse, in the way it's often formulated, I find to be intellectually very unsatisfying. As it's often presented, it's almost Panglossy. There are many possible universes. This is the best of all possible universes, and everything is for the best. That's also called the anthropic principle. I like, well, as a scientist, I like working on things that can fail. As noted in the introduction, I spent a few years before I worked on WMAP working on ideas that, when the Kolbe results came out, I knew were wrong. On one hand, it was disappointing to spend 5 years of your life on something that just turned out to be an idea. It wasn't incorrectly calculated. It was a theory about how the universe worked that doesn't describe the universe. It was possibly right, turned out not to be. So I like ideas that can fail. And the multiverse is one that I think is not even an interesting idea. If you were visiting Stanford or Cambridge, England, they would speak very differently of the multiverse. But most of us in Princeton don't. Yeah.
When you said that the universe is flat, is there thickness and what's the ratio?
The universe is a three-dimensional thing, so it's not really a thickness in that sense. When we talk about the geometry, all right, so let's talk about two-dimensional systems first, because those are easier to visualize. If I have a flat piece of paper, if I draw a circle, I make the radius of the circle bigger, the circumference gets larger. You remember high school geometry, circumference is 2 pi r. The bigger you make the radius, the bigger the circumference is. Now let's think about, for this I wish I had a ball, but visualize a sphere right here. You go around the North Pole, you go out a little distance, you draw a circle. The bigger the radius is, the bigger the circle. As you go around the sphere, you'll notice, as you get to the equator, the circumference doesn't get any bigger, right? You can't, you draw, I'm not a great artist. One circle, I draw the next circle, the next circle. If it's a sphere, the sphere has a maximum radius at the equator. And then it starts getting smaller again. So that on a sphere, there's a maximum size. Now, in 3 dimensions, to do the same experiment, you have to think about not a circle with a given circumference, but the surface area of a sphere. So if I go out a certain distance, I draw a sphere around me that's, say, 10 feet in radius. There's surface area of that sphere goes as 4 pi r squared. The further I go out, the bigger the sphere gets. If space is flat, what that means is that the geometry is such that the sphere, the surface area, continues to grow as 4 pi r squared. The bigger the diameter, the bigger the radius, the more surface area on the sphere. However, that's true in flat space. The geometry of space is what we call closed or positively curved. It would be the 3-dimensional analog of the globe, 2-dimensional surface of the sphere. And as you went further and further out, you'd reach a maximum size, then it would start getting smaller again. So that if space, that describes it in terms of its radius. The other way to visualize it is in terms of the triangles. So on this blackboard, the sum of the angles in a triangle are 180 degrees. On the surface of a sphere, the sum is bigger. You can do that, draw those triangles not just in flat space, but we can take string, if you like, or better, light rays, and go from us to our galaxy to other galaxies and measure the geometry of space that way. Now, this is in fact what we do with the microwave sky. We know how big the average hotspot is. If space is flat, those hotspots are about a degree across. On the other hand, if there was more matter in the universe, more matter curves light. That would make the trajectories that light takes as it goes from our satellite back in time would be curved like that. So the same size hotspot, physical size, would look like a spot that might be bigger, perhaps 2 degrees across. So that's how we measure the geometry and see different geometries depending on the density of the universe. So this is a dense universe, less dense. This is what we call flat. And it's not flat in that it's a 2-dimensional surface, but flat in that the rules of geometry that work on a flat piece of paper in 2 dimensions here work in 3 dimensions in terms of the way angles work and distances work. Yeah?
You described the universe starting out as very, very uniform.
Mm-hmm.
And then you describe it as getting more lumpy, more complex.
Mm-hmm.
Don't you have, it seems like to me that the entropy is going the wrong way. You're going from very high entropy, or for low entropy to higher entropy.
No, you're going from low entropy.
Low entropy to higher entropy.
Because it's very dense, but very ordered. Very dense and, but uniform temperature. And as it evolves, it gets more structure, more disorder. And so entropy is increasing. So there's 3 arrows of time, all point in the same direction. One arrow of time is the expansion of the universe. The universe is going from a dense state to a less dense state. The second arrow is that driven by entropy. The universe starts out in a very ordered state, becomes more disordered with time, entropy increases. And finally, there's the psychological arrow of time. We remember the past, not the future. Right? Yeah.
It seems like the big thing now is to figure out what the nature of black matter and energy is.
Dark matter, yeah.
Right, if you do that, the next question is, where did it come from? According to Lawrence Krauss, it came from nothing. But his definition of nothing is mind-boggling. You
Yeah.
familiar with that?
Yeah, I know Lawrence very well, yes. I wouldn't say it's Lawrence's concept. Lawrence is a great popularizer. He's not really a great scientist.
He explains pretty well, except I can't figure out what nothing really means.
Well, so there's two different, where does dark matter come from? There's a related question, where do atoms come from? Right, so there's why is there protons and not antiprotons? Why is there the amount of dark matter? Different ideas, so there's several different parts of this question, actually, all of which are interesting. One part is we start out with this hot, dense universe, filled initially with basically heat. Why does matter emerge out of that? Why do we have stable particles, and why do we have the abundance we see? That's an idea that we think we might have some answers to. If the dark matter particles interact pretty weakly, you end up creating them, and as the universe becomes less dense, they can't find each other to destroy themselves. So that the fact that we have long-lived particles that do not destroy themselves is connected to the idea that the universe is expanding. Now, this question of why is there anything, why is there matter at all, where does the energy come from, is connected, is really another version of the question of how did the universe begin? What was the cause of that initial energy? One notion for how the universe began is to start with a state that was initially empty, this nothingness. And out of that empty state, to suddenly start the Big Bang explosion. I'm thinking of trying to think of a nice, a familiar physical analog. A lot like if you have a lot of moisture in the air, and suddenly you start to nucleate raindrops. And you'll sometimes see raindrops emerge out of a clear sky. On a very humid day, it'll sometimes almost spontaneously rain as droplets come forth. And that kind of spontaneous nucleation could happen when the lower energy possibility is not to have humidity, but to have raindrops. You actually create energy by going from humidity to raindrops. Some of that energy comes out sometimes in things like lightning. So there's energy available to do that. So that's that kind of nucleation event is the kind of thing that people model when you think, let's start with this empty nothingness, which is basically effectively a human space that in which in that case the laws of physics are such that it would rather change states and form little regions of energy, those little water droplets. And the Big Bang in that particular model is a water droplet. Now, this is an idea that is very speculative. I think it's important in this talking about these subjects to differentiate between things that we have very strong observational evidence for, the idea that the universe is expanding, the idea that we know reasonably well what happened from 400,000 years after the Big Bang to today, to the question of what happened in the first minute or the first microsecond of the Big Bang, or what was there before the Big Bang. When we start to deal with those questions of why is there a Big Bang, why is there stuff, we're now crossing from areas in which we have a pretty good understanding that we've put together over the past, say, well, in many ways going back to the work of Einstein. In the, 1917.
Metaphysical.
It gets into the metaphysical. Yeah.
If you were to go back to your origin, you keep going back until you get to minute one, 1 second, half a second, you're getting to a point where it's infinitely dense, infinitely small. I would have to assume at that point that general relativity or any kind of relativity doesn't apply, more quantum would apply. And from what I understand, if we're looking at quantum mechanics, things happen from nothing. At least we can't figure out why they happen.
Well, no, we understand. So you go back in time, as you've noted, the further back you go in time, the hotter the universe gets, the denser it gets. Back about 300,000 years before the Big Bang, after the Big Bang, we're talking about the microwave background, the temperature is about 3,000 degrees. That's the kind of temperature people achieve in their laboratories here all the time. That's relatively easy to study. You know, get your oven up to 500 degrees after we're home. You understand the physics pretty well. You go back to about a minute after the Big Bang, you're getting to energies and temperatures that are probed in big accelerators. And so we actually understand that a minute after the Big Bang reasonably well. In fact, we can understand how helium and deuterium was produced in those early moments. You go back about a second after the Big Bang. That's about, you're getting now close to times that the big accelerators are just getting to now for a second. But the further back you go, once you go back to a millionth of a second, you're now at energies well beyond what we can get at the lab. And that means our knowledge of physics starts to get more and more speculative. And as you note, the further back we go, the higher the densities and temperatures get. We get back to 10 to the minus 43 seconds after the Big Bang. So really early. You get to such enormous densities and temperatures that our understanding of how to do calculations in physics start to break down. They break down for just the very reason that you mentioned. And I like to think of it that we had really two great ideas in 20th century physics. General relativity, theory of the universe on its largest scales, we've been talking about tonight. Quantum mechanics, which is actually a very predictable theory, works very well describing the behavior of things on small scales, atoms, transistors. And these two great 20th century ideas each work really well in their own realm. What we're struggling with is how to combine them together to have a successful theory of quantum gravity. And indeed, if we're going to understand what happened in this first 10 to the minus 43 seconds, and have a chance to figure out what happens before the Big Bang, or if there's a before, we need a quantum gravity theory that's successful. What has been the major thrust of theoretical particle physics in much of the last 20 years is an idea called string theory. And string theory represents an attempt to develop a fully consistent theory of quantum gravity. And it's been a very powerful theory. It taught us lots of new mathematics and developed lots of new techniques. But it's not yet a successful theory, in that it's not yet produced a definitive theory of quantum gravity that makes experimental predictions that you can test. It's not for the lack of trying. Some of the smartest people I know have devoted much of their scientific career to developing this theory. In many ways, I feel as a cosmologist, until they do that, I don't really have the tools that we need to describe what the answer to this question of what happened in the first moments. What did the universe emerge from nothing? Did time begin with the Big Bang? I don't know. And I think it becomes a very hard question to answer right now without the right theoretical tools. You know, it's akin to Henry Norris Russell and others tried to understand stars in the 1920s and understand how stars shined. But they didn't know about nuclear fusion. They didn't realize you could burn hydrogen to helium. They thought elements existed forever. So they were missing a really important bit of physics. Nuclear physics wasn't discovered yet. And you really can't do stellar evolution until you understand nuclear physics. So I think my own prejudice is that we're not going to be able to understand the very first moments of the Big Bang until we have a well-developed theory of quantum gravity. So on that,
Thank you very much, David.